So this is the equation. So basically, the equation of this one, the uh, IV characteristics. Now, what happens if we plot this one? Uh, if we plot the VDS ID versus this VDS, so this is basically the ID. So ID versus VDS. So this is basically a parabola, right? If you plot it, it will be a parabola, right? For different VGS, so this VGS has a small parabola, then the parabola increases, and and if my VGS is big, so it's something like this. So now we want to find out what is this maximum point of this parabola. So to find out, just we can just differentiate this ID with VDS. So if I do this partial differentiation, ID with VDS, so and if I make this as 0, right? If I just differentiate it, it's a simple differentiation. So I think what I will get here is B1 COX W by L. So if I differentiate this, this will become 1. So it will be something like VGS minus VTH minus VDS, right? Now if I make this as 0, sorry, excuse me. So if I make this as 0, so we'll get this point where when, like, if this is 0, right, when this VDS is equal to VGS minus VTH, right? So whenever this VGS minus VTH, VDS is equal to VGS minus VTH, we get this maximum point of this parabola, right? We'll get this maximum point of the parabola. Now if you see here, if you observe here, if I keep increasing the VDS, it is seen that in this parabola it goes and it comes down to 0. So it seems that the current will come down to 0 after some time, right? But in actual scenario, this doesn't happen, right? What happens is after this point, the current will not start decreasing, rather it will stay almost constant. So this is what it is observed, right? So this theory is valid only till this point, only till the maximum point, is derivation. But after this, it is seen that this derivation or this equation is not valid anymore, because what happens, this current starts becoming constant, right? Then how do we reason out for this? So to do that, what happens basically is like, right, this current equation, whatever the equation that we have derived, is only valid for this much, but after this the current starts becomes constant. So that's why this region is called the saturation region. Why it happens? Because you see here, as soon as the VGS minus VTH is this VDS become VGS minus VTH, then what happens is the potential difference here at this node becomes 0, because we know that to form a channel, VGS minus VTH is required, and because this VDS is equal to VGS minus VTH, that's why no channel will be formed here. So pinch off. So basically, because of which at this point, like that, no channel will be formed. Now if I increase this VDS further, hello, everyone is hearing me, right? Hello, hello.
Yes, sir.
Yeah. I got this notification that I have a bad network, so I just want to make sure that I'm audible to everyone. So now if I increase this VDS further, VGS minus VTH, this channel will start reducing. Why? Because here the potential is greater than VGS minus VTH. Now only at this point it will be the VG, because again there will be a gradient, potential gradient here, because this potential is much higher here. so even higher than this Vg. So only at this point the potential will be equivalent to Vgs minus Vth. So we can see here at this point only the potential will be Vgs minus Vth. So that's why only from this onwards there will be no channel in this region like that. So because of this formation, because of this pinch off formation, what happens is the current becomes constant. The current becomes constant. So one can tell, okay, if there is this no channel, no region, how the current is flowing. So what happens, because this depletion, because this is of very high potential, so whatever the electrons are here, it just gets swept because of this. There's a depletion region here basically. So just whenever it just crosses this barrier, because this is a very high positive potential, and electrons are always attracted towards the positive potential. So there is there is a flow of these electrons to this depletion region. Okay. So, and because of which we have this saturation region and currents get saturated. So so the saturation current we can get from this point. So here,
Sir,
yes,
so the electron flow will be from left to right or right to left? It will be from left to right, right?
it will from left to right, definitely, yes, definitely from left to right, right, because this is higher potential, so the electrons will go to the higher potential, right?
So
But
then there should be a balance, right? Like why the pinch off is coming, like the decrease of electrons at the right side.
why it is coming?
Yes, I
uh,
guess I think like the electrons should increase at this side, right side also.
where at this right side?
Yes, sir.
Oh, no, because here the channel is not formed, right? Because as I have mentioned, at this point, if you see this, the to form a channel, we need a potential difference between this gate and this region, right? So if you see here, this potential is higher than this Vg, right? So because of which there will channel will not be formed in this region, right? Are you able to get my point? Huh?
No, sir.
It's not clear, right? Okay, let me zoom it here. Okay, so is it clear? Hello. So you
Like I
see,
didn't understand.
yes,
I didn't understand like why this like pin like the electrons are flowing from left to right. That is okay, but this pinch off like the like why there is lot of electrons on this left side than right side, because there should be balanced side, because this side also the electron movement is here, right side. Like the electrons are flowing from left to right,
true.
so then why the electrons at the right side, why the number of electrons at the right side is decreasing?
Okay, so basically what happens is here we have a lot of density of electrons. So actually in actual region what happens, there is a depletion region here, because what happens is this I am not showing here because this is a PN junction, right? PN junction will have this depletion layer, right? Right? The depletion charges are here. So this depletion charges will be there. I am not going too much in detail, but this pinch up is happening. You are getting this point, right? Why pinch up is happening? Because if you see at this node and at this node, the potential difference is very high, which is this is at ground and this is Vg. So because of which lot of these charges will be formed here, right? A lot of free electrons. But at this node or at this node, this is even higher. So the potential difference here is very small. So because of which these charges are not formed. Only at this region, because there is again decrease in the potential from this direction, so only at this region, this is a region where the potential difference, or this potential at this node is Vgs minus Vth. So again, so there is a zero potential here. So but from there again the potential keeps decreasing. So there is a potential difference. So the channel are formed. I got your question. So if a fixed amount of current is flowing, why this there is a distribution in charge. A constant current will flow, but what will happen? There will be a gradient in the charge formation. All the charges will not be definitely flowing, right? Did I answer your question?
Yes, sir.
Yeah. So there will be a flow of current, but because of the potential gradient that is formed, right? Here there is a zero potential, and here this is VDS, right? So there is a potential gradient that is forming like that. Potential difference. It's a gradient. It's not just a fixed potential difference. Because of this gradient, that's why this kind of charge formation is happening. Like that. Is it clear? Or
Yes, sir.
okay. So now we know that at this point we can find out what is the current. So at this point, the if you just plug in the VDS should be VGS minus VTH. So if I just plug in this VDS at this equation, what I will get is ID equal to mu n COX W by L VGS minus VTH whole square. So this is just if I just plug in this one, this VDS value here, so I'll get this kind of equation here, right? So if I summarize here, if I take the summary, what I'll get is so in this region, whatever the equation that we have derived, that mu n CX WL VGS minus VTH minus half VDS square, this is valid for this region. This region is also called as linear region. This linear region. And at this point, as we have derived, this is the maximum point, and this we can find out by differentiating this one with respect to VDS, and then we'll get that VDS equal to VGS minus VTH. And if I just plug in this equation, then I get this I'll get this kind of equation where ID is equal to half mu n COX W by L VGS minus VTH whole square. So this is for the saturation region. Is it clear? Any questions again here at this point of time, till this point of time? Is there any question? Hello?
No, sir.
Okay, so basically I have got these two equations. Now we'll come to this an important point. So if you observe here, this is L dash, not L, right? Why is it is L dash? Because if you see the length of the channel, whatever the derivation that you have done, it has decreased from L. So this is supposed to be L. This is L, right? The whole channel length is L, but now because of this pinch off, it has decreased to L dash, right? L dash because of this pinch off, the channel length has decreased. So because of which, I cannot write L here. I have to write L dash. Then only this equation will be valid. But then how do we find this L dash? I have to write in terms of L, right? So we can find out this L dash in terms of L. We can write down this L dash in terms of L. So these equations need to modify. So as I have mentioned here, this is my L dash, and this is the total L. So I can write L dash as L minus delta L. So delta L is this one, right? Delta L is this one, and I can write this L dash as L minus delta L. Now if I just do some simple mathematical simplification, what I will get is, if I take the inverse of this one, 1 by L dash will be equal to 1 by, if if I take this common L, 1 minus delta L by L, right? And it also can be written as 1 by L, 1 minus delta L by L inverse. Now, if this delta L by L is very very small, small compared to 1, then I can do this approximation, right? Simple approximation. I can take this minus 1 before. What I will get is 1 by L dash is almost equal to 1 by L, 1 plus delta L by L, right? Now this delta by L is directly proportional to VDS. So this no, so this delta L by L is directly proportional to VDS, right? So what we can introduce some proportionally constant. So what we'll get is delta L by L is, there is this one constant is introduced, which is lambda VDS, right? Now if I just use this equation back here, I can just plug in back here, then what I will get is 1 by L dash is equal to 1 by L 1 plus lambda VDS. Now if I just so I can write 1 by L dash as 1 by L 1 plus lambda VDS. So if I just replace this 1 by L dash here, 1 by L dash here with this value, what finally I'll get is I'll get this kind of equation for my triode region or linear region, and the linear region is also called as triode region. And in the saturation region, what I'll get is ID equal to half mu n Cox WIL VGS minus VTH 1 plus lambda VDS. So this is what I will get in the this is what I will get for the equation of the MOSFET. So these are the two basic current equation. I know all of you are familiar with this. So I'm just repeating this again and again. So in the linear region, it is mu n Cox WL VGS minus VTH VDS half VDS square, and in the saturation region, it's ID equal to half mu n Cox WL VGS minus VTH square. So now we have this 1 plus lambda VDS. So what it is showing is that with increase in VDS, there is a slight increase in the current. So which we can see from this graph, right? Which you can see from this graph, right? It is supposed to remain constant, but actually because of this pinch off, right? Because of this pinch off and because this pinch off being significant to compared to L, right? There is this slight increment in the current. So now as we go to a very low technology node, right? So when we go for the very lower technology node, 65 nanometer, 28 nanometer, because the channel length has reduced a lot, we cannot neglect this lambda, right? Because this pinch off region becomes a very significant portion of the total L. So because of which in a very higher technology node, right, this lambda becomes a very important factor. So what happens is this lambda becomes so large, right? Lambda becomes large. So because of which we don't get this constant kind of equation. So it affects a lot of the performance of the transistor a lot, especially when we have to design some in analog circuits, when we have to design very high gain. The high gain achievement of high gain becomes very difficult because of this issue like that. So when you read about this analog circuit, you will see that because of this, getting a very high gain becomes very difficult because the lambda is very significant in higher technology. Like that. Any questions till this point?
No, sir.
Other people able to follow till whatever we have discussed till now? Everyone following?
Yes,
Or
sir. Yes, sir.
it's
Yes, sir.
complicated, or it's too easy, or it's repetition?
Yes, sir.
Uh,
Sir, I have a doubt.
yes. What is the
Sir,
doubt? Yeah.
here we are disconnecting the channel from drain to source.
Mm-hmm.
Yes, and current is flowing.
Yes. Yes.
Yes, sir. Then again we are increasing VDS. This channel will be depleted. If somehow we can reduce the whole channel, then there is still a current.
I didn't follow you. Like, can you just repeat it? Like the last one, that you, last
Sir,
sentence. Yeah.
I'm saying that increasing VDS,
Mm-hmm.
we are disconnecting the channel from drain to source.
Okay. Basically, the pinch off is happening. Yes. Pinch off is
Yes,
happening.
sir.
Yes.
If
Yes.
we are going to increase VDS so high, that's the whole channel is depleted.
Okay. So you are telling that this is become very short, something like that.
Yeah, yes, sir. Very short. Then
Yeah.
the current is constant or is going to vary, sir.
Okay, so that's why I mentioned, right? So if you see this graph, right? If I am increasing this VDS very high, so you see we are not getting a constant current. That's what I'm telling, right? So the pinch off is happening. So if as this pinch off becomes shorter and shorter because of this high potential, right? What we are getting here is the current is increasing basically. It's not constant, it's increasing. And if my this channel length is very small, this pinch off is becoming very significant, right? This pinch off is becoming significant, this delta is becoming significant. So in that situation what it is happening is basically the current is increasing more, like that. Did I answer you? Did I answer your question?
Sir, excuse me, sir. Sir, first we have created the channel
Okay.
applying VGS minus VGS greater than VTH
Okay.
to flow the current.
Okay.
Yes, sir. But
Mm-hmm.
again we start depleting the channel.
Okay.
If
Mm-hmm.
somehow we can deplete the whole channel after
Okay.
increasing VDS,
Okay.
then there is a current or not?
Oh, there will be current like that. There will be current like that.
Sir,
Yeah,
how,
yeah.
sir?
Uh-huh.
Sir, how? Because there is no channel.
Okay. So what happens is, there will be channel. Definitely, it's not that there will be no channel. There will be a small channel form like that. So what happens is actually this is a PN junction. If I actually, if we want to know this more in detail, I think you can read more in detail of the PN junction. So what happens is this is a PN junction, right? This is a PN junction. So actually there is this formation of, there will be a formation of a depletion layer here, because this
Yes.
is right, in a PN junction there is a depletion layer, right? Whenever I have this PN junction, right? This is P N, right? So there is we have this depletion layer, right? So the electrons here will come here and we'll have this negative charges formation here, right? And a positive charge will be formed here. Following, you could follow me, right? Hello, hello.
Yes. Yes, sir.
Yeah. So because this is a P substrate and N, so because of which there will be this formation of this PN junction here, and what happens as soon as it will be formed till here. Actually, there it will be formation of till here. So what happens because of this large potential here, large positive potential, these electrons, as soon as this little bit process this barrier and it goes to this depletion region, they will be swept off by the large this positive potential like that. So because of which there is a flow of the you know flow of the current. Now what happens is if you increase it, definitely this pinch off will come closer and closer, and this depletion region also will be going higher and higher. Getting right? So, and because of which there will be a flow of current. Even though this channel has been, there is no, it seems to be like there is no channel, but we have to understand that there is a depletion layer forming, and as this potential increase higher and higher, this depletion region also will be increasing higher and higher. So for that, I think we need to go a little bit to the basics of the device like that. But here I don't want to discuss too much. You can read yourself like that. So because it's mostly the circuit class, right?
Yes.
So I don't want to go too much in detail away. But your question is very right, like that. So when this channel is formed, so we should understand. Although it is not shown here, but simultaneously a depletion layer is also getting formed, right? So because of this reverse bias is get because whenever I am increasing this potential, the reverse bias is also getting increased. So because of which the PN junction, this depletion layer, this formation is also becoming higher and higher. And as soon as it crosses this depletion layer, as soon as the electron starts, so this large potential, actually this is quite similar to the operation of the BJT also, right? So BJT, we say that the whenever the there is a whenever the electron crosses from emitter to the base, because of the large potential of the collector, the carriers are swept away, right? If you remember how the working principle of the BJT. So similar kind of stuffs happen here. Okay. So now I hope I clarified your doubt. I know I know it's not very clear, but if you want, you can little bit you can read about it like that, about how the that BJT operation happens and all, how this carrier are swept. So all those things are there. Like it's a very good concept, good to understand the stuff. But yeah, like that. So now whenever this so the saturation is region is a region. So if you see here, this is the V, this is the S, and this is the drain, and this is the gate, right? So whenever this gate potential is lower than the drain, then we have this saturation region, basically saturation region. And when this is and this drain and this gate voltage are equal even, so this node just represent the equal, like it's just showing that this is higher and this is lower. So whenever they are just equal, it is also still the saturation region. But as long as the gate potent like whenever the gate is higher than the drain by VTH or VTN, it is MOSFET, so VTN, and this notation is used. So then what happens? The transistor enters into the triad region. So just by remembering this, we can understand, or we can remember the the two regions of operation. So now whenever this gate is higher than the drain by VTH, then it enters into the triad region. But whenever, as long as the gate potential is lower than the drain, then even if it is equal, then it is in saturation region. Okay. So for PMOS also it is same. The same formula applies, right? So of course, we have to use a mod here, right? Because it will be VSG instead of VGS. So and the threshold voltage may also become negative. So just by using a mod here, you can use the same formula, right? Just take care of the potential difference, like so PMOS, this node will be lower than the source, right? Gate will be lower than the source, and this is the drain. So whenever this drain is a very low potential, much lower than the gate, then it is in saturation region. So even if they are equal here, again this is also in saturation region. But whenever the gate is much lower than the drain, then it goes to the triad region. So whenever this is lower than the threshold voltage, then it goes to the triad region. So sometimes we get confused. Okay, the equations for the PMOS and NMOS are different, or taking care of signs. So don't worry at all. My suggestion is just take the mode of it and do the same analysis as NMOS. that. So don't worry about the notations and all. Just take the magnitude of it and use the same way of doing the analysis like that. Is it clear? Hello?
Yes, sir.
I know today's class was little bit
It's
complicated because of lot of derivations and other stuffs. But I think next class onwards things will be more interesting. Anyways, so now whenever whenever the if you zoom in here, if you zoom in into the linear region, whenever the VDS is very small, right? Whenever the VDS is very small, right? Especially whenever the VDS is lesser than much lesser than twice of VGS minus VTH, right? So if this term is very small, so this becomes dominant, right? So when VDS is very small, I can ignore this term. So I can ignore this term. So only this term becomes prominent. So this is like VDS is much lesser than twice into VGS minus VTH. Then I can approximate ID as mu n COX W by L VGS minus VTH. So this is in this region. So the VDS is very small. So then what happens if I just divide this VDS by ID, I will get this kind of expression of R on. So in this region, whenever the VDS is very small, the MOSFET acts like a simple resistance, a simple resistor. So you can see there is it's a very linear, like it's a very the current is increasing linearly with the voltage. So which is same as saying it's acting like a simple passive resistor, which is true in the sense that, right? Because what happens is, if we see here, what happens is whenever this is, I think let's go back. So here, what happens when this potential is very small? The channel is almost constant. Like there is no gradient of this one. There is no gradient. So because of which it's like acting like a simple resistance like that. So the charges are flowing through this, and it has some resistivity like that. So and this resistivity is directly controlled by the gate potential. So the higher the gate potential, like that, lower will be the resistivity because there will be more number of carriers. So, but if the voltage is lower, VGS is lower, the carriers are less, and higher will be the resistivity. Like that. Following, follow this point. So this point is useful. Yeah. Hello.
yes, sir. No, sir.
Okay. Okay. So this concept is sometimes useful. This approximation is sometimes useful whenever we come to the situation when VDS is very small. Then this approximation is generally used. Okay. Now I think the uh, time is almost over. So it's 11 to. Sorry, I started little late, 10 minutes. Next time we'll try to start in time. And what we'll do in the next class, we'll learn about the body effect. So we'll see what is this body effect. We'll try to understand this expression of the body effect, how the threshold voltage varies with the uh, the with the body effect, and how this situation arises. Like although we say that the all the bulk is shared in all the NMOS share the same bulk, so they share the same substrate, but there are situations where this body effect arises like that. So that's why it's also necessary to, even if we are not using some separate body for its PMOS, NMOS, still this body effect arises in some circuit configuration. So it is necessary to understand this body effect and what are its consequences and or influences. Okay, so I suggest if you can read the initial chapters of this book Rajavi. Although this book is for analog device design, but I feel the initial chapters of discussing about the MOSFET is very interesting. So next day we'll understand body effect. We'll understand the different parasitic capacitance that is there in a MOSFET and how all it varies with the whenever it's going from triode to saturation region, how it varies. So I think that will complete the whole discussion of the characteristics of MOSFET. Then after that we'll come to the characteristics of inverters. Like that. Okay, thank you everyone. If you don't have any questions, it's 11:05 now, so I'll
Thank you,
end the
sir.
class. Yeah, thank you.
Thank you, sir.
Mm.